We got just a few more examples to complete this chapter on probability. So let's look at this next example. Suppose 1,000 raffle tickets are sold at $5 each. So we have 2 first place tickets with a $200 prize, 5 second place tickets with a $100 prize, and 10 third place tickets with a $50 prize. Find the expected value of the net gain to the customer. So now, in this example, X is going to represent the net gain. Now, in these types of game problems, you have to be careful and determine if this is a game where you have to pay first to play or you don't pay first to play. Well, in this game, you actually have to pay first because you have to buy a ticket. So, in other words, if you lose, if you don't win anything, then you don't break even. You actually lose $5. So your net gain would be -5. If you win the third place prize, you don't actually gain. Your net gain is not $50. Your net gain is $50 less the $5 you paid for the ticket. So your net gain is $45. And then if you win the $100 prize, similarly your net gain would be $95, and if you win the $200 prize, your net gain would be $195. So now, if you want to find out the probability of each of these net gains, it's actually going to be the probability that you win that particular prize. So it might be easier for us to work backwards. Let's find the probability that you get a net gain of $195. In other words, what's the probability that you win the $200 prize? Well, there's only 2 tickets that will lead you to that prize. So if you buy 1 ticket, then you have a chance of 2 out of 1,000 to win that prize, or 0.002. Now let's find the probability that your net gain is $95, or that you win the $100 prize. Well, if you look at the $100 prize, there's 5 of those tickets. So your chances of winning those is going to be 5 out of 1,000, which is 0.005. And then what's the probability that you win the $50 prize, or have a net gain of $45? Well, there's 10 of those, so that would be 10 out of 1,000, which is 0.01. Now, then the probability that you lose $5, well, obviously that's going to be very high. Now, I got 983 out of 1,000, which is 0.983. Well, some of you might ask, well, where did you get 983? Well, it's like this. You've got 10 tickets that win the $50 prize, 5 win the $100 prize, and 2 win the $200 prize. Well, that means there's going to be 10 plus 5 plus 2, 17 winners. So if you take 1,000 tickets and subtract off the 17 winners, you're going to get 983 losers. So there's 983 people, or 983 tickets that is, that's actually going to have a net gain of -$5. Now, well, now that we know the probabilities of these 4 net gains, we can now put it in a probability distribution table, but with games we call this a payoff table, and we can find the probable payoff. So if you multiply -5 times 0.983, and then 45 times 0.01, and then 95 times 0.005, and then 195 times 0.002, and add those together, you get -$3.60. So that means that the average ticket buyer, the average person that buys a ticket, is going to lose $3.60. So basically you can easily figure out what the game's going to profit, because if you sell a ticket, if you sell 1,000 tickets and each ticket averages a loss of $3.60, then just multiply $3.60 by 1,000 and that'll tell you what you're going to profit. One note here, a game is fair if the expected value of the game is 0. Obviously this game is unfair, but if you think about it, why would anyone have a fair game if they were trying to make money? So if someone's trying to make money, then the game's definitely going to be unfair to the consumer. You know, kind of like if you go to a casino and try to play a particular game in a casino, well, you can bet all of those games are unfair because they're trying to make money. Okay, so here we have another example similar to the light bulb example. This time we have batteries, 20 batteries, and 2 of those batteries are dead. We're going to take a random sample of 3 batteries and test them. So let's let X be the hang on a second, a random sample of 2 batteries and test them. Okay, sorry. Okay, so let's let X be the random variable associated with the number of dead batteries in the sample and find the expected value of X. Okay, hang on just a second because let's see. Yeah, I am taking a random sample of 3 batteries. I'm sorry. I was looking at the answer and I confused myself for a minute. Okay, but I'll explain this for you so you can understand it. Alright, so let X be the random variable associated with the number of dead batteries in the sample. Find the expected value of X. Well, the reason that X can't go up to 3 here, and that's what threw me off, because I saw this going to 2 and I just immediately thought I meant to say 2, a random sample of 2, but actually I remembered it's okay if I take a random sample of 3, because if I take a random sample of 3, I still can't get more than 2 dead batteries, and the reason is because there's only 2 dead batteries in the population here. So even though I'm taking 3, so even if I took 10 battery samples, I couldn't get more than 2 dead batteries in a sample. So anyway, the possibilities for the number of dead batteries are 0, 1, or 2 dead batteries. Now, that should say 2. I know that. Alright. So anyway, the probability of 0 dead batteries, well, that would mean if I'm taking a sample of 3, then out of the 18 good batteries, all 3 must be good batteries. And then out of the 2 bad batteries, I'm choosing none. Now if I want the probability of getting 1 dead battery, well, notice here, out of the 2 dead batteries, I'm choosing 1. Now to finish this out though, out of the 18 good batteries, I'd have to choose 2. And then to get 2 dead batteries, then out of the 18 good batteries, I would choose none, and out of the 2 dead batteries, I would choose 2. Okay? Now, the denominator in each of these, and that's what actually cued me in that I was taking a sample of 3. The denominator is actually 20 batteries choose 3. So the number of samples possible would be 20 choose 3. So you divide each of these numerators by 20 choose 3 to get your answers for the probabilities. So then I get 0.716 here, 0.268 here, and 0.016 here. Now if you add those 3 up, they should add up to 1. And then the expected value would be 0 times 0.716, 1 times 0.268, 2 times 0.016. So the expected number of dead batteries in the sample is 0.3. So if we did this experiment over and over and over and over and over, then we would expect to average 0.3 dead batteries per trial. Okay, you can read this note here, but I've already alluded to what I've got written in red here. So you can just read that yourself and then move on when you're through reading it. Okay, let's talk about a venue. A rock concert producer has scheduled an outdoor concert for a particular day. If it does not rain, the producer should make $20,000 from the concert. If it does rain, the producer will be forced to cancel the concert and will lose $12,000. So, the producer has learned from the weather service that the probability of rain is a 40% chance, or 0.4. So find and interpret the producer's expected profit. Well, actually, if you think about here, there's 2 things that can happen. If it rains, then he's going to lose $12,000. And if it doesn't rain, he's going to actually profit $20,000. So, let's look at the probability of rain. The probability of rain is a 40% chance. So there's a 40% chance that he loses $12,000. So that means the probability of no rain would be a 60% chance. So there's a 60% chance that he's going to gain $20,000. Well, when you multiply these together, negative 12,000 times 0.4 plus 20,000 times 0.6, and you add those together, you get $7,200. So the expected value suggests that the vendor should not cancel, but this assumes there will be many more concerts under these same conditions. Now remember, for an expected value to work out in the long run, you actually have to assume that you're going to have many trials. So that's something that just makes sense. It's just like a baseball player that's batting a particular percentage. Well, if he goes 0 for 4 one game, then that's basically 0%, but that doesn't mean that his batting average is 0, because the batting average is determined over a long time period. Okay, I've got a couple more examples here. I may not get but one of these in, but let's go ahead and talk about them. Okay, so let's look at another game. Alright, suppose you were offered a chance to play the following game. I'll deal you 3 cards from a standard deck. If you get no face cards, you pay me $5. If you get 1 face card, I'll pay you $2. If you get 2 face cards, I'll pay you $10. And if you get 3 face cards, I pay you $15. Now, what do you think your expected winnings would be on average? Well, let's take a look. Let's take a look at the possibilities here. Right here are the possible winnings. So now this game you don't actually pay to play, so we can just consider the possible winnings here are -5. You could lose 5, win 2, lose 10, or win 15. And this is how it works. To lose $5 would be the same as the probability that you get no face cards. And we calculated this earlier as 0.4471. To win $2 is the same as the probability of getting 1 face card, and we calculated it earlier to be 0.4235. To win $10 is the same as the probability of getting 2 face cards, and that's 0.1195. And to win $15 is the same as the probability of getting 3 face cards, which is 0.01. Now let's multiply each of these payoffs by the probabilities. -5 times 0.4471, and let's see, that should be a 1, not a -5. And then 1 times 0.4235, and then 10 times 0.1195, and then 15 times 0.01. Now, if you add that up, you're actually going to get -$0.04, which is a loss of 4 cents. So that means I will average a 4-cent profit per game. Now, it doesn't sound like much, but if I can get 1,000 people to play this game 50 times an hour, 24 hours per day, then I can expect a daily profit of over $48,000. And this is how casinos get rich. They let just enough win to keep people coming back. Last one. Now, roulette's fairly a simple game, but there's a lot of different ways you can play it. So I'm just going to look at one way. Roulette has 18 red numbers, 18 black numbers, and 2 green numbers. If you bet $1 on black, you get $1 back, plus you win $1 if it lands on black. Otherwise, you lose the $1 that you bet. So what is the expected gain? Well, you know that you'll either lose $1 or gain $1. So -1, 1. Well, what's the probability you lose $1? Well, if you're going to bet on black, then there's 18 red and 2 greens that will cause you to lose money. So that's 20 out of 38 probability. And then the probability that you win $1 would be the 18 black. So 18 out of 38 is the probability. And now if you calculate the expected value of that, you take -1 times 20 over 38 plus 1 times 18 over 38, and you get -2 over 38, which is about a nickel. So the expected player, the player is expected to lose a nickel per trial. And now you can freeze the video and read these notes at the bottom. It might give you a little more insight. And then you can close it out when you're done, because I'm finished with this chapter.